Welcome to ECE 3300 at the University of Utah. In lecture number 20, we're going to talk about the gradient and Laplacian operators and how they are used to find the electric field and the potential. Here are the major concepts of the gradient. The gradient gives us the directional derivative of a function. For instance, the gradient of the potential tells us how the potential varies in the x, y, or z direction. If we had a function something like this, and that was our potential function, and let's say that's the potential as a function of x, then we would be able to find the derivative at several of these different points. That's the slope. The derivative of the voltage with respect to x is the gradient in the x direction. Then, if this were a two-dimensional function, we would have variation in the x direction, the y direction, and in 3 dimensions the z direction as well, and the gradient would tell us the slope of the line or the variation in each of those directions separately. You probably are very familiar with the gradient in rectangular coordinates, having calculated that in your calculus class. And here is the function for the gradient in the cylindrical and the spherical coordinates as well. The thing to note is in cylindrical coordinates, note that right here we have a 1 over r function in front of the derivative with respect to phi, and that over here in the spherical coordinates we have that in front of the theta term, and we have the 1 over r sine theta in front of the phi term. The back of your book has these functions so that when you need to make the calculation of gradient in any of our coordinate systems, you can easily refer to these equations. The electric field is minus the gradient of the potential. What that means is the electric field is represented by the change of the potential. So let's consider the function that I just drew a minute ago, which is the potential and how it varies in the x direction. The slope of this line is the electric field in the x direction. So the slope of this line is Ex here. The slope would be Ex, 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 Ex. So you can see that the electric field is stronger at this location than it is here. When the electric field is strong, the potential has a lot of variance. The gradient of the the gradient of the potential, remember, gives us the derivative of the potential in the x direction. This right here is the Ex term, plus the derivative of the potential in the y direction, and that gives us the Ey term, plus the derivative of the potential in the z direction, and that gives us the Ez term. Put a minus sign in front of every one of these, and you'll have the right vector format. Now we also can find the potential from the electric field using essentially the same equation. Here's an equation that tells us how the potential can be calculated from the electric field. What it says is take the electric field and integrate along a line between the two potential points that you are interested in. For instance, let's say that right here we have a VA and right here we have a VB. We are interested in finding the electric field between them. We know it happens to be the slope of that line. So what we're going to do is take the electric field and integrate it along the line between VA and VB. And that's going to give us the potential difference. So if we had an electric field right here at point A, and we had another electric field right here at point B, we would integrate along a line between A and B, put a minus sign there, and that would tell us the difference between VB here and VA there. Now I'm going to mention that you could go along that line, or you could go along this line, or you could go along any line, doesn't need to be a straight line, between points A and B, and you would get exactly the same answer. The potential difference would still be the same.